Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic we're going to look at approximating solutions to higher order initial value problems. So in this topic we will start by discussing second order initial value problems. We will then explain how to reformulate a second order initial value problem into a system of two first order initial value problems. However, that's already something that we can solve. So we will look at an example. We will then consider a fifth order initial value problem and reformulate that problem into a system of 5 first order initial value problems. This technique, of course, generalizes for any higher order initial value problem. Now in your calculus course, you've already seen second order initial value problems that are usually written in this format. We have a function of t times the second derivative of y plus another function in t times the first derivative plus a function in t times y of t, and that is equated to some forcing function. You also have two initial conditions. So at time t equals or t naught, the value of the function is y naught, and at time t naught, the derivative is some given slope. Note the notation that we are using for the constant of the initial derivative. There is no function of t there. It is the initial slope. Well, based on the implicit function theorem, which we saw before, we can always write, well, almost always write a higher order initial value problem as follows. We have that the nth derivative of the function y is some expression in terms of t, y of t, the first derivative of t, all the way up to the nth minus first derivative of t. Also, we now need n initial conditions because when we have the nth derivative, we must integrate n times, and each integration requires one additional constraint or introduces a coefficient of integration, which we must constrain with the initial conditions. So therefore the initial conditions are the value of the function at t naught, the value of the derivative, the value of the second derivative, and so on and so forth up until the value of the nth minus first derivative of the solution at t naught. Consequently, we can take any second order initial value problem and write the ODE in the form the second derivative of y is some function in t, y of t, and the derivative of y at t. We also have the two initial conditions, which are required. Now, we don't know what y of t is, and we don't know what its derivative is. Let's assume that these are two different functions we're trying to solve for. All right, so we are going to represent y of t by a new function w naught. W naught is a function of t, and we're trying to approximate it. But we also have the derivative of y of t, and we will represent that with w1 of t. So in trying to find the solution to this initial value problem, we are going to re-represent it as a problem where we want to find both functions w0 and w1. Okay, note therefore that if we take the derivative of w0, w0 was defined as y of t. So therefore, the derivative of w0 is the derivative of y of t. But wait a second, look at the right-hand side. The derivative of y of t is the function that we described as w1. Now, the derivative of w1 is, well, the derivative of y of t, which is the second derivative of y. Now, what's the second derivative of y? Well, going back to the ODE, the second derivative of y is the function on the right-hand side of that equation. But wait a second, y of t was w0, and the derivative of y of t was w1. So now we have that the derivative of w1 is a function of t, w0, and w1. Not only that, w0 at time t0 is just y at t0, which is the initial position. w1 at t0 is just the derivative at t0, which is the initial slope. All right. So now we've reformulated a second order initial value problem as a different problem. We have two first order initial value problems, and we are trying to find both w0 and w1. Now, ideally, in the end, when we differentiate w0, we should really get w1. But we've now reformulated the problem. All right, consequently, a second order initial value problem can be written as a system of two first order initial value problems. So essentially, here are the two ordinary differential equations, and there are the initial conditions. In the last topic, we saw that we could rewrite a system of first order initial problems using vectors. So essentially now, the vector valued function w of t is a two-dimensional vector containing the solutions w0 and w1. The derivative of this vector w is w1, and whatever the right-hand side of the original ordinary differential equation was, evaluated at t, w0, and w1. And we have our initial conditions. Let us look at converting this generic second-order initial value problem into functions that we can feed into our initial problem solvers. So again, we saw in the last topic how we can write this using vectors. So the right-hand side will be a function capital F that takes a time variable and a vector variable. The vector is two-dimensional. It returns the vector w1 because the derivative of w0 is w1, and then it returns a function f with the independent variable t and the vector w passed to it. In this case, suppose that the differential equation was the second derivative is twice the first derivative minus the function plus sine of t. So in this case, therefore, the function little f would take t as a first argument, w as a second argument, and it would return 2 times w1 minus w0 plus sine of t. All right, that would be it. Now here's a specific initial value problem. Now this is the way that you would normally write it in your course in calculus. On the left-hand side you have the homogeneous ODE, and this is equated now to a forcing function, in this case sine of t, on the right-hand side. Now we would write this as a vector valued function, as you see here, and now we are moving everything other than the second derivative to the right-hand side. So now it becomes negative 2 times w1, w1 representing the derivative of y of t, minus then again w0, which represents y of t itself plus the forcing function, in this case sine of t. All right, we can now find the solution to this using the techniques in calculus, but on top of that, we are going to enter this into our DP45 approximator. So here we've obviously chosen an h value that is initially too small, as it seems as if h is more or less doubling with every single next iteration. However, notice afterwards that if the function is reasonably smooth, the distance between the values, the h value, becomes larger, whereas near the maxima and minima, the distance between the h values is ever so slightly smaller. Again, this is because we need a smaller h value to get sufficient accuracy. So now, one thing that's important to note here are how we interpret the results. All right, let's look at the output. Now, here we see in the first column the t values. So as you can see, we start with an h value of 0.101, and then it's doubled to 0.2, and then doubled again and again and again and again. So we obviously start with too small an h value, but that's okay. At least we underestimated rather than overestimated. Notice also you can guess what the maximum h value I allowed. Notice that between 1.27 and 2.27 is a distance of exactly 1, which is not twice the previous h value. So it's very unlikely that would happen by chance, except that the maximum h value was indeed 1. Now, the third argument returned, recalling that the first argument returned was the number of points, 16 in this case. The third 16 intervals. The third is a vector of the two solutions, or approximations thereunto, at the t values. So the first one is W0 and and the second is W1. So the first column, or the first entry of the vector, is what we plotted on the last slide, because that is the solution, or the approximation of the solution to y of t. The second entry of the vector is W1, and you'll recall W1 was an approximation of the derivative of y. So we can actually plot t versus the second vector, or the second entry of the vector. In that case, we get the plot here, and you will notice that it very closely follows the derivative of y of t as shown above. Now, this is the same process that we would use for a higher order initial value problem. For example, here we see a fifth order initial value problem, and therefore there are 5 initial conditions. We have to convert this to a function. So once again, we have a vector w with entries 0 through 4. And of course, the derivative of w0 is w1. The derivative of w1 is w2. The derivative of w2 is w3. The derivative of w3 is w4. However, the derivative of w4 is w5. Where do we get that? That is from the ordinary differential equation. So what we have to do is bring everything to the other side and isolate the fifth derivative. So that's what we see there. We see cos of t minus 17.5 times w4, that is the fourth derivative, minus 132.625 times the w3, which represents the third derivative, and so on and so forth. And finally, we must divide all of that by 12.5, the coefficient in front of the fifth derivative. Now here we can actually make use of this, where we will approximate a solution using our dp45 function. So we begin by simply declaring the local variable result to be whatever type is returned by dp45. That is, as you remember, a tuple where the first entry is the number of intervals, the second entry is an array of the t-values, the third entry is an array of vectors, each of them 5-dimensional, with approximations of the W0 through W4 functions at the corresponding t-value, and of course W0 is an approximation of y, W1 is an approximation of the derivative, and so on and so forth. So that's what's returned. Now the first argument is of course the function pointer to the function we just defined above. The second argument is a pair of t-values, the initial t-value and the final t-value. Here is a 5-dimensional vector with the 5 initial conditions. Here's an array that specifies both the minimum and maximum h value we are willing to tolerate, and we will start with the geometric mean of these, which happens to be 10 to the negative 2. Finally, here is the maximum allowable error per unit time. Since we're going from 0 to 10, then we should expect an error no worse than 0.1 at the end of this. Now, as I said, we are looking at the result. It's a tuple. The first entry of the tuple, which we retrieve through get0, is of type unsigned int, and it is the number of intervals. In this case, it happens to be 32. Then we have a for loop. This is the t-value, and we print each of the t-values from k going from 0 up until and including n. And these are the w vectors at the corresponding t-values. Now the only entry in these w vectors we really care about is the first, because the first entry is the value corresponding to y. And here is the actual solution to that fifth order initial value problem, and you can see the approximation points. Again, initially h is too small, so it starts doubling, but after a while, again, you can see if the solution is reasonably flat, the points seem to be slightly wider or further apart, and near the maxima and minima, or where there's significant curvature, it seems as if the h values are slightly closer together. But again, here we see the actual solution to that fifth order initial value problem, and we see the approximation using the Dormand-Prince algorithm. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!